Everyone. This is our theoretical session for the laboratory manual inorganic pharmacy 2 lab. Today we are going to discuss about the theoretical part for the experiment number 3C, and the name of the experiment is qualitative analysis, that is identification of group 3 cations. Okay, let's start with the principle. The principle states that salts are compounds which are formed from the reaction between acids and bases. For example, sodium chloride, it is a salt which can be formed from the reaction between hydrochloric acid and sodium hydroxide. Hydrochloric acid is an acid and sodium hydroxide is a base. And what is inorganic salt? You know that an inorganic salt is just a salt which has no organic part in its molecular structure. Just like sodium chloride, it do not contains any organic part in its molecular structure. And we can say that any salt is composed of two parts, cation and anion. In case of sodium chloride, the cation is sodium plus and anion is chloride minus. The cation part usually comes from the base and the anion part usually comes from the acid. In case of sodium chloride, if we talk about the cation, that is sodium chloride, which comes from the sodium hydroxide base, and if we talk about the anion, which is chloride anion, which comes from the hydrochloric acid. So we can say that the cation part usually comes from the base and the anion part usually comes from the acid. Now, based on the solubility characteristics, the common inorganic salt or inorganic cations, and you know that cations are usually metal, so we can say that usually metal in nature are classified into 5 groups. And how does the grouping occurs? That was discussed in our previous lecture. Cations of each group is precipitated a common reagent. So by stepwise addition of those reagents, we can first identify which group the cation belongs to. Then by using specific reagents, we can confirm the cation. The common inorganic cations can be classified into 5 groups based on the solubility characteristics. Cations of each class are precipitated by a specific reagent. If we have already clarified this term, cations of 5 group are precipitated by a common reagent. For example, the cations of group 1 are those cations which will be precipitated by dilute hydrochloric acid. If we add dilute hydrochloric acid in the sample solution, and if the sample solution gives us a precipitate, then we can say that this solution might contain group 1 cations. Then if we add hydrochloric acid in the sample solution and the sample solution do not gives us any precipitate, then we have to supply or add hydrogen sulfide gas in that solution that is already treated with hydrochloric acid. If treating with hydrogen sulfide gas produces any precipitate, then we can say that this precipitate might contain group 2 cations, and these are the group 2 cations. And going forward, if we add hydrochloric acid in the sample solution, and if it do not gives us any precipitate, then we add hydrogen sulfide gas in the solution and it fails to produce any prominent precipitate, then we have to add ammonium chloride and excess ammonium hydroxide. Conversely, we can add sodium hydroxide and ammonium hydroxide, and if sodium hydroxide, ammonium hydroxide, or ammonium chloride or excess ammonium hydroxide produces any precipitate, then we can say that this solution might contain group 3 cations, and these are the group 3 cations. And if all these above things, dilute hydrochloric acid, hydrogen sulfide, ammonium chloride, ammonium hydroxide, fails to produce any precipitate, then we have to add ammonium carbonate, or conversely we can add sodium carbonate. And if ammonium carbonate or sodium carbonate produces the precipitate, then we can say that this solution contains the group 4 cations and which contains these cations. And if no PPT appears even after addition of ammonium carbonate or sodium carbonate, then we can say that this solution contains group 5 cations, and group 5 cations are these ones. So in our previous lecture we discussed about the identification of group 1 and group 2 cations. How does the group 1 and group 2 cations were discussed? If you have forgotten those things, you might take a glimpse of that lecture too, which is available in our YouTube video channel. Now today we are going to talk about or the identification of group 2 cations. You know that we have to take for the detection of group 3 cations. At first we have to take the sample solution, then we have to add hydrogen sulfide hydrochloric acid, dilute hydrochloric acid in that sample solution. After addition of hydrochloric acid in the sample solution, if PPT do not appears, then we have to add hydrogen sulfide gas in that sample solution. And if addition of hydrochloric acid followed by hydrogen sulfide gas do not produces any PPT, afterwards we have to add ammonium chloride in the presence of excess ammonium hydroxide. If the group 3 cations are present, then there will be a apparent PPT. So we can say that cations of group 3 are not precipitated by dilute hydrochloric acid or hydrogen sulfide gas, but they can be precipitated from a salt solution by the addition of ammonium chloride in the presence of excess ammonium hydroxide. With this reagent, hydroxide or sulfide salts of cation will be precipitated. If the precipitate is formed, then confirmation test should be performed to identify specific cation. That this line implies that after the addition of hydrochloric acid there will be no PPT. After the addition of hydrogen sulfide gas there will be no PPT, but after the addition of ammonium chloride in the presence of excess ammonium hydroxide there will be PPT. If there appears PPT, we can say that this is group 3 cations. Then we have to go for the individual test to confirm which group 3 cation is present within this salt. Let's look at the video how does the group 3 cations are identified, group identification. We are going to test for the presence of group 3 cations. At first we would take the sample solution in the test tube. Into the sample solution we would add dilute hydrochloric acid. We are taking the sample solution in the test tube. So sample solution. Now into this sample solution we will add dilute, that means 6 molar hydrochloric acid. If PPT appears, then it would be an indicative for the presence of group 1 cation. If PPT do not appear, then it may be group 2, group 3, group 4, etc. The PPT didn't appear, indicating that group 1 cation is absent. Now we are going to add or apply hydrogen sulfide gas into this test tube. If PPT appears, then it would be an indicative for the presence of group 2 cations. Now we are applying hydrogen sulfide gas into this hydrochloric acid containing sample solution. Apparently there is no PPT. The amount of gas applying to the solution should be great in amount, so we are applying large amount of gas, so there passes huge amount of hydrogen sulfide gas is passing through this test tube, and there is no PPT. This indicates that there is no presence of group 2 cations. Now we would go for the test that will confirm us whether it is group 3 or group 4. Start. Now into this hydrogen sulfide containing test tube we are going to apply ammonium hydroxide, 9M ammonium hydroxide. If group 3 is present, then there will be a PPT. There is black color PPT indicating that the presence of group 3 cations, and this indicates the presence of group 3 cations. That's all for the confirmatory. That's all for the presence of group 3 cations. Hope you have understood how the group 3 cations are identified. This is the group test for the group 3 cations. Now we have to go for individual test to identify which cation is present within this salt. I must say that we would have been used ammonium chloride if there was no PPT after the addition of ammonium hydroxide. Sorry. Okay. Now let's move on the individual test for the confirmatory test of group 3 cations. First of all, we will talk about the confirmatory test of ferrous ion, that is Fe2 plus test. Okay, if dilute sodium hydroxide is added to a solution containing ferrous ion, a green gelatinous PPT of iron 2 hydroxide will form. If sodium hydroxide is added to a solution containing ferrous sulfate or ferrous 2 ion, then a green gelatinous PPT of ferrous hydroxide will form. Excess addition of sodium hydroxide will not dissolve the PPT. There will be no reaction. So this is a confirmatory test for the presence of group ferrous ion. Another test is that when dilute ammonia is added to a solution containing ferrous ion, then a green PPT is formed. A green PPT of ferrous hydroxide is formed. Then if we add excess amount of ammonium hydroxide in this green PPT containing solution, then the PPT do not dissolve. That means there is no reaction between the excess ammonium hydroxide and the ferrous hydroxide so produced. This will an indicative of the presence of ferrous ion. The third test is that to confirm the presence of ferrous ion, we have to add potassium ferricyanide in the sample solution. If the addition of potassium ferricyanide produces blue PPT, then it will be an indicative of the presence of ferrous ion. So let's review this again. We have to add sodium hydroxide in the sample solution. It will produce a green PPT of ferrous hydroxide, and excess amount of sodium hydroxide addition will not cause solubilization of the PPT. Again, we have to take a fresh 2 ml solution and we have to add ammonium hydroxide in that solution. This will also produce green PPT, and the PPT will be insoluble in excess ammonium hydroxide. For further confirmation, we have to take another 2 ml sample solution and we have to add very small amount of potassium ferricyanide, and addition of potassium ferricyanide will produce blue PPT. Now let's look at how does the presence of ferrous ion is confirmed in the laboratory. We are going to test for the ferrous ion. We have taken 2 ml sample solution in this test tube. Now we are going to add 2 m dilute sodium hydroxide into this test tube. This will produce light green gelatinous precipitate. This is light green gelatinous precipitate. We can see that this is light green gelatinous precipitate. So this is an indicative of the presence of ferrous ion, and the PPT is insoluble in excess amount of alkali. If we add excess amount of alkali, the PPT will not dissolve, and this is prominent from this addition that as the amount of sodium hydroxide increases, the PPT also increases. That means the PPT is not going to dissolve with the excess amount of alkali. We have taken another 2 ml sample solution in another test tube. Now we are going to add dilute, that means 2 m sodium hydroxide solution in this test tube. This will produce light green gelatinous precipitate. This is gelatinous precipitate. The difference between the addition of sodium hydroxide and ammonium hydroxide is that the PPT of sodium hydroxide was about surrounding the entire solution, but the PPT of ammonium hydroxide is floating at the top of this solution. This is light green gelatinous precipitate of ammonium hydroxide, addition of ammonium hydroxide that produces ferrous hydroxide, and the PPT will also be insoluble with excess amount of ammonium hydroxide. Add excess ammonium hydroxide, he is adding excess amount of ammonium hydroxide, and the PPT is insoluble. As the amount of ammonium hydroxide is increasing, the PPT is also increasing. So this is an indicative of the presence of ferrous ion. This is another famous test for the detection of ferrous ion. We have taken 2 ml sample solution in the test tube. Now we are going to add just 1 drop potassium ferricyanide into this test tube, and this will produce a light blue color. This is light blue color. This is the confirmatory test for the presence of ferrous ion. So this is all about the presence of detection of ferrous ion. Thank you. Hope you have understood how the ferrous ion is detected in the sample solution. Now let's move on the detection for the ferric ion. If dilute sodium hydroxide is added to a solution containing ferrous ion, then a brownish red gelatinous precipitate of ferric hydroxide will form. When sodium hydroxide is added to a solution containing ferric ion, then a reddish brown precipitate, which is gelatinous in nature, will form. Excess addition of sodium hydroxide in the solution will not dissolve the PPT. There will be no reaction. Okay. Now, if a solution contains ferric ion, and if we add dilute ammonium hydroxide into that solution, this will also produces reddish brown PPT, and which is not insoluble when excess ammonium hydroxide is added. Okay, now let's move on to our next experiment. To confirm the presence of ferric ion, if we add potassium ferricyanide to a solution containing ferric ion, then a deep brown PPT or deep greenish precipitate of ferric ferricyanide is obtained. Finally, if we add potassium thiocyanate in a solution containing ferric ion, then a blood red color is formed due to the formation of ferric sulfocyanide. Okay, let's review the topics again. We have to take 2 ml sample solution, then we have to add dilute sodium hydroxide to the sample solution. If there appears a reddish brown precipitate, then we can say that this solution might contain ferric ion. We have to add excess amount of sodium hydroxide, but the excess amount of sodium hydroxide will not solubilize the PPT, indicating the presence of ferric ion. Then we have to take another sample solution. Then and in that sample solution we have to add ammonium hydroxide. If ammonium hydroxide addition produces reddish brown PPT, this will also indicate the presence of ferric ion, and excess addition of ammonium hydroxide will also not solubilize the PPT. That means there is no reaction between the reddish brown precipitate and ammonium hydroxide. Then we have to take another sample solution. And into that sample solution we have to add potassium ferricyanide. This will produce a greenish precipitate due to the formation of ferric ferricyanide. Okay, and then finally we have to take another sample solution and we have to add potassium thiocyanate. This addition of potassium thiocyanate will produce a blood red complex due to the formation of ferric sulfocyanide. Now let's have a look how the presence of ferric ion is confirmed in the laboratory. In 2 ml sample solution, now we are going to test for the ferric ion. Now we are going to add just 0.5 ml 2m sodium hydroxide into this sample solution. This will produce light brownish gelatinous PPT. This is light brownish gelatinous PPT, and the PPT is insoluble in excess amount of alkali. Increased addition of alkali will not dissolve the precipitate, and we can see that it is prominent that the PPT is insoluble in excess alkali. As the amount of alkali increases, the PPT also increases. So this is light gelatinous PPT, and this is an indicative of the presence of ferric ion. We have taken another 2 ml sample solution. Into this sample solution, in this time we are going to add dilute ammonium hydroxide, 2m ammonium hydroxide, and this will also produce brownish red PPT. And like the ferrous, the PPT is floating at the above of the solution. In case of alkali, sodium hydroxide, the PPT was was wandering throughout the solution, but in case of ammonia, the PPT is floating at the top of the solution. This is also light brown in color, and excess amount of ammonium hydroxide will not dissolve the PPT, and we can see that as the amount of ammonium hydroxide increases, the PPT also increases, indicating that the presence of ferric ion. We have taken another 2 ml sample solution. In this time we are going to add potassium ferricyanate K3FeCN6. This will produce green color. This is prominent green color. This indicates the presence of ferrous ion. This is our final confirmatory test for the presence of ferric ion. In the sample solution we are going to add potassium thiocyanate. 1 drop of potassium thiocyanate. This will produce a blood red coloration. This is a blood red color. So this is a confirmatory test for this was all about the confirmatory test of ferric ion, and this indicates the presence of ferric ion. Thanks. Hope you have understood how the ferric ion is confirmed in the sample solution. Now let's move on our another confirmatory test, which will confirm the presence of zinc ion in the sample solution. Okay. When dilute sodium hydroxide is added to a solution containing zinc ion, a gelatinous PPT of zinc hydroxide is produced, which is white in color. Okay. If excess amount of sodium hydroxide is added to the solution containing white zinc PPT, then the PPT becomes dissolved due to the formation of sodium zincate, or a complex which is known as Na2ZnO2 or sodium zincate. Okay, now we have to take another sample solution, and we have to in the solution which was treated with sodium hydroxide, and the solution which produced zinc hydroxide, white PPT of zinc hydroxide, and after the addition of excess amount of sodium hydroxide, the zinc hydroxide will solubilize, forming a complex known as sodium zincate or Na2ZnO2. Then we have to, after the solubilization of zinc, solubilization of white PPT, then we have to apply hydrogen sulfide gas in the test tube. If we apply hydrogen sulfide gas, then it will cause reappearance of the white PPT due to the formation of zinc sulfide. That means this will form a zinc sulfide complex which is white in color, and this will be an indicative of the presence of zinc ion. Okay, let me clarify these things again. We have to take a sample solution, and we have to add sodium hydroxide in that sample solution. Sodium hydroxide will react with the zinc. If the sample solution contains zinc, sodium hydroxide will react with the zinc and will produce a white PPT of zinc hydroxide. Then we have to add excess amount of sodium hydroxide in that PPT containing solution. Excess amount of sodium hydroxide will react with the PPT and will form a soluble complex which is known as sodium zincate. Then after the complete dissolution of the sodium zinc hydroxide PPT due to the formation of sodium zincate, then we have to apply hydrogen sulfide gas in that test tube. Hydrogen sulfide gas will react with the soluble complex as Na2ZnO2 or sodium zincate and will produce zinc sulfide. Zinc sulfide is white in color. So the PPT first appears, then disappears, and again after the reaction, after treating with hydrogen sulfide, again it reappears. Okay, this is one of the confirmatory tests for the presence of zinc ion. Okay, another test is that when dilute ammonia is added to a solution containing zinc ion, then what happens? Then dilute ammonia will react with the zinc ion and will produce a white gelatinous PPT of zinc hydroxide. And if we add excess amount of dilute ammonia in that solution containing white PPT of zinc hydroxide, the excess ammonia will react with this PPT, that means zinc hydroxide, and will dissolve or solubilize the PPT, forming a compound which is known as tetraamine zinc ion, Okay, let me clarify the topic. Second, we have to take 2 ml sample solution in a test tube. Then we have to add ammonium hydroxide in that solution. This will produce a white gelatinous PPT. Then we have to add excess amount of ammonium hydroxide. This excess ammonium hydroxide will cause solubilization of the PPT, forming a soluble complex known as tetraamine zinc ion. Okay, now let's have a look how the presence of zinc ion is confirmed in the laboratory. Sample solution. In this case, we are going to test for the presence of zinc ion. The presence of zinc and aluminium is quite similar. Now we are going to add dilute ammonia in this solution. This will produce white PPT. We are going to add this dilute 2m ammonium hydroxide into this solution. This will produce white PPT. White PPT appears, but the excess amount of ammonium hydroxide will cause to dissolve the PPT. Excess amount of ammonia will dissolve the PPT. PPT dissolves. This is an indicative of the presence of zinc ion. Remember that the PPT didn't dissolve in case of aluminium when ammonium hydroxide was added, but in case of zinc ion, the PPT which appears due to the presence of zinc ion by the ammonium hydroxide dissolves when excess amount of ammonia is added. This is an indicative of the presence of zinc ion. Sample solution. In this case, we are going to test for the presence of zinc ion. The presence of zinc and aluminium is quite similar. Now we are going to add dilute ammonia in this solution. This will produce white PPT. We are going to add this dilute to that was a test for the presence of zinc ion, and we have another test which will demonstrate how the zinc ion is tested by using sodium hydroxide and hydrogen sulfide gas. Let's take a look how the zinc ion is tested by sodium hydroxide. We are going to test for the presence of zinc ion. In this case, we have taken 2 ml sample solution and we are going to add dilute, that means 2 m sodium hydroxide solution into this solution. Sample solution. This will cause the presence. This will produce white PPT, and the PPT appears. This is the presence of PPT, white PPT. The PPT will dissolve, and you can see that this is the white PPT which is formed by the addition of sodium hydroxide. This white PPT is due to the formation of zinc hydroxide, which is produced by the reaction of zinc with sodium hydroxide. When excess amount of alkali is added, this is the presence of PPT, and the PPT dissolves by the presence of excess amount of alkali. Didn't dissolve yet. This is a clear solution, indicates the presence of zinc ion. The PPT will reappear when hydrogen sulfide gas is blown through this solution. And we are going to add hydrogen sulfide gas into this solution, and this will cause reappearance of the PPT and will be an indicative of the presence of zinc ion. Applying the hydrogen sulfide gas in the test tube, this will cause the reappearance of the PPT. The PPT reappears. We can see that the PPT reappears, and certainly this is an indicative of the presence of zinc ion. That's all from the group 3 cations. Okay, now let's talk about the detection test for the presence of aluminum ion. When dilute sodium hydroxide is added to a solution containing aluminum ion, then it produces a white gelatinous PPT of aluminum hydroxide, indicating the presence of aluminum hydroxide. Then if excess amount of sodium hydroxide is added to the solution containing white PPT of aluminum hydroxide, this will cause the solubilization of the PPT, forming a soluble complex known as sodium meta-aluminate. Then after the production of a soluble complex clear solution, we have to add ammonium chloride followed by heating. This will result the reappearance of the PPT. Okay, let me clarify the term. We have to add sodium hydroxide in the solution containing aluminum. If aluminum is present, this will produce a white PPT. After the formation of PPT, we have to add excess amount of sodium hydroxide. Excess amount of sodium hydroxide will solubilize the PPT, forming a soluble complex known as sodium meta-aluminate. Then we have to add ammonium chloride in that solution, and we have to heat the solution. After heating, there will reappear the PPT. That means first the PPT appears with reaction with sodium hydroxide, then the PPT disappears when excess amount of sodium hydroxide is added. Again, when ammonium chloride is added and heated, the PPT again reappears. This is one of the confirmatory tests for the presence of aluminum ion. Now, another test. We have to take another sample solution in another test tube. Then we have to add ammonium chloride in that ammonium hydroxide in that solution. This will produce a white gelatinous PPT of aluminum hydroxide. Then we have to add excess amount of ammonium hydroxide, but the excess amount of ammonium hydroxide will not solubilize the PPT of aluminum hydroxide. This is quite different from the zinc cation. In case of zinc, when ammonium hydroxide is added, zinc cation also produces white PPT, but excess amount of ammonium hydroxide solubilizes the PPT that was formed by the reaction of zinc with the ammonium. That means zinc hydroxide is solubilizes when excess ammonium is added, but aluminum hydroxide do not solubilizes when excess ammonium hydroxide is added. Now let us take a look how does the presence of aluminum hydroxide is confirmed in the laboratory. Take 1 ml sample solution in a test tube. This is the test for aluminum. Now in this sample solution we are going to add dilute sodium hydroxide. This will produce white PPT. This is white PPT, and the PPT will be soluble in excess alkali. In this case we are going to add concentrated sodium hydroxide so that the solubilization will take at a faster rate. The PPT will dissolve in this excess alkali clear solution. This is an indicative of the presence of aluminum ion. Now in this solution we are going to add ammonium chloride, and we are going to heat this solution. Already PPT appears, and heating will faster the appearance of PPT. Now we are heating this solution in the water bath. We can see that the PPT is appearing at a faster rate. The PPT reappears. This is an indicative of the presence of aluminum ion. We are taking the sample solution again, 1 ml sample solution in the test tube. Into this sample solution, we will add dilute ammonia. This will produce white PPT, and in this case the PPT will not dissolve when the white PPT appears. Excess amount of addition of ammonium hydroxide will not cause the solubilization of this PPT. We are adding excess amount of ammonium, the PPT will not dissolve. This is an indicative of the presence of aluminum ion. The test for the presence of for the confirmatory test for the presence of aluminum ion, 1 ml of sample solution has been taken in the test tube. Into this sample solution we are going to add few drops of 2m dilute ammonium hydroxide. This will produce white PPT, and the PPT will not dissolve upon the addition of excess amount of ammonium. Now in this case we are going to add 9m ammonia. We are going to add 9m ammonium hydroxide to this PPT. The PPT will not dissolve. PPT doesn't dissolve. This is an indicative of the presence of aluminum ion, and this also confirms the presence of aluminum ion. Hope you have understood the test for the presence of aluminum ion and zinc ion. There is a difference between the test of zinc ion and aluminum ion, and in case of zinc ion you can see that PPT dissolves. This is an indicative of the presence of, this will produce white PPT. We are going to add this dilute 2m ammonium hydroxide into this solution. This will produce white PPT. White PPT appears, but the excess amount of ammonium hydroxide will cause to dissolve the PPT. Excess amount of ammonia will dissolve the PPT. PPT dissolves. This is an indicative of the presence of zinc ion. Remember that the PPT didn't dissolve in case of aluminum when ammonium hydroxide was added, but in case of zinc ion, the PPT which appears due to the presence of zinc ion by the ammonium hydroxide dissolves when excess amount of ammonia is added. That's all for this moment. Hope you have understood how the group 3 cations are tested. Thanks to all for watching.